This picture shows a promotional event organized by Genesis. They used over 3,200 illuminated drones for a light show in Shanghai to announce their arrival in China. What do we think when we see this? This is undoubtedly one of the coolest promotional events, and certainly a display of what autonomous drones are capable of. I had similar thoughts as well. At the same time, I was worried. The thought that struck to me is, how secure are these drones? What happens if an attack is launched when there are over 3,000 target systems and, as we see, a large crowd has gathered to watch the show? Hi everyone, I'm Pritam, PhD student at University of British Columbia. In this talk, I will present the gaps in current security mechanisms for autonomous robotic vehicles and our experience in developing low-cost attack recovery techniques that ensure safety in robotic vehicles. Robotic vehicles, RV in short, rely extensively on sensors for perception and decision-making. Correct measurement of physical state is paramount for deriving appropriate actuator commands. For example, an autonomous ground vehicle relies on GPS to derive current position and navigate accordingly. And in the same way, an autonomous drone relies on gyroscope or accelerometer sensors to determine its velocity, angular orientation, and fly accordingly. Unfortunately, RVs have been shown vulnerable to attacks that raise concerns. We focus on sensor attacks, which cannot be prevented by traditional software security techniques like memory isolation or crypto. Examples of physical attacks are GPS spoofing, where the RV's position is manipulated by transmitting malicious signals, and signal injection attack that injects acoustic or magnetic noise signals to manipulate sensors from an external source. Sensor attacks are not just limited to academic papers. We have seen these types of attacks launched against military navigation systems. For example, it is suspected that one of the Lockheed Martin drones used by the US military was hijacked in 2011 through a GPS spoofing attack. In a recent incident, a UK warship's position was falsified near a Russian base in Crimea. These attacks are a looming risk for industrial RVs. Something that further exaggerates the risk is the attacker can be a complete outsider without any network or system access and still cause malfunctions by emitting malicious signals from an external source. And as RVs are expected to operate in urban environment, attacks against industrial RVs can cause damages and injuries. As we have seen that it is important to secure RVs, let's take a look at what has been done so far to secure RVs and what are the gaps in the current solutions. A lot of prior work in this domain has gone into developing attack detection technique, anomaly detection techniques, etc. The state-of-the-art techniques rely on invariants or models to detect attacks. If an invariant is not satisfied during an RV mission, or if the model predictions and the real-time behavior of the RV are way off, the attack detector raises an alert. And these techniques are very effective in detecting attack. In many cases, they detect attack with 100% true positive and 0 false negatives, which is pretty good. However, attacks are often launched when the RV is in motion. So even if the attack is detected, it cannot prevent the consequences. Therefore, a detection technique is only good for raising alert. It's not a complete solution. Some RV manufacturers use secondary hardware to trigger failsafe once an attack is detected. The idea here is the secondary set of hardwares do not rely on sensors, and they are only meant to perform emergency operations. However, this strategy opens new vulnerabilities. Now attackers can exploit this to disrupt and abort RV missions, causing a denial of service. Further, landing in an arbitrary or hostile territory, in case of drones, is not really desirable. So the key question that still remains unanswered is, how should we respond once an attack is detected, and how to ensure safety? As robotic vehicles interact with us in the physical world, the goal must be to develop attack-resilient countermeasures and not just detection. In this talk, I will present two low-cost software solutions to recover RVs from sensor attacks. Low cost means these techniques do not require any hardware change, and it incurs low performance and energy overhead. And these systems are generally very resource constrained, so ensuring low overhead is really important. The first technique I will present today uses a feedforward control, and the second technique uses historic state replay to recover RVs from attacks. Before jumping into the techniques, let's get a little bit of background and understand RV's internals and see how attacks disrupt these systems. RV's internal can be broadly classified into physical components, such as motors, sensors, etc., and cyber components, which are dedicated programs for navigation, control, and other autonomous functions. RVs rely on sensors to derive actuator signals, such as motor thrust, and they use a PID control, which operates in a feedback loop to minimize environmental noise. Let's take an example to quickly understand this. Consider a scenario where a gush of wind deviated a drone slightly from its trajectory. The PID control receives the actual state information accounting for the deviation from the trajectory, and it increases the motor thrust to compensate for that error and brings the RV back on track. This measurement and compensation-based error correction strategy that PID uses is extremely effective in transient environmental errors like wind gush. Now, let's see what happens to the PID controller under an attack. Unlike environmental noise or faults, attacks are not transient in nature. This graph here shows that trajectory in error incurred due to a GPS spoofing attack during a drone mission. The y-axis shows that trajectory error, and the x-axis shows how the error increases as the attack progresses. Normally, the error will be 0, but however, as we see in this figure, the drone incurs persistent and systematic error throughout the mission, which prompts the PID controller, because it measures and compensates. In this case, it measures the systematic error, but ends up overcompensating for the attack-induced error, which results in erroneous actuator signals, and eventually it crashes the RV. So what we learn is PID's measurement and compensation-based error correction, which is effective in handling faults, becomes undesirable under attacks. We do not blame PID control for the consequences of the attack. It was never really meant to handle attack-induced errors. However, this analysis shows that for a long time, we have considered false resilience in designing autonomous systems, and we have sort of overlooked attacks. So now we know that attacks induce persistent error in sensor measurements, which prompts PID controller to overcompensate, eventually leading to erroneous actuator signals. Based on this observation, we derive two recovery requirements. In order to recover RVs from attacks, we will have to handle the persistent error, which attacks tend to manipulate the sensors. And we will have to derive safe actuator signals to maneuver the RV under an attack. To achieve these recovery requirements, we designed a feed-forward controller using machine learning. And unlike PID, which is a feedback controller, the feed-forward controller do not measure and compensate, so it doesn't suffer from the same problem that PID suffers from. Instead, the FFC anticipates the error by correlating past and present sensor measurements and takes corrective actions preemptively. Thus, the FFC takes the current sensor measurements and the given waypoint, and under an attack, it will predict robust actuator signals. We design a framework in which we run FFC in tandem with the PID control. Both the FFC and PID predict actuator signals in a time series. We monitor the deviation between both the predictions to flag an attack. Once an attack is detected, we switch to FFC's prediction. As we know, it predicts robust actuator signals under attack, hence able to recover the RV. And once the attack subsides, we switch back to PID. By using PID and FFC in tandem, our framework offers best of both worlds and protect the RV from faults and attacks. That is, PID protects from environmental noise, faults, and FFC protects it from the attack. We perform extensive analysis on the feed-forward control recovery technique on both simulated and real RV systems. And we find this technique is actually really good in recovering RV from attacks. It prevents crashes in all the cases. It ensures mission success despite the attacks and incurs very low performance and energy overhead. But we also find that this technique is only effective when a single sensor is under attack at a time, not effective when multiple sensors are attacked simultaneously. Examples of multiple sensor attacks are, imagine an attack where both the camera and LiDAR are manipulated in a coordinated way, or the GPS and gyroscope sensor of a RV is manipulated simultaneously. Recovery from these strong attacks is a much harder problem to solve. What makes it more challenging is now the RV cannot rely on the correctness of other sensors. We try to understand the attacker's capabilities in performing this type of strong attacks. Because the attack relies on emitting malicious signals to manipulate the sensors, realistically the attack will be confined to a range. After a certain range, the malicious signals will faint and they won't be strong enough to manipulate the sensors. Based on that observation, we derive our recovery goal. And the goal is to prevent immediate disruptions due to multiple sensor attacks and safely maneuver the RV out of the attack zone. So imagine the curly brace that we see in this figure is the attack zone, and as long as we prevent disruption within that zone, we are good. As we know that sensor manipulation leads to erroneous physical states and results in erroneous actuator signals, and we know that if we satisfy these two recovery requirements, we should be able to maneuver the RV out of the attack zone. To prevent erroneous physical states due to multiple sensor attacks, first we identify the sensors that are under attack, and we isolate those sensors from the control process. We don't use the sensor readings anymore, and this will prevent erroneous physical states due to the attack. But simply removing a stream of inputs in a feedback control loop will lead to erroneous actuator signal and cause disruptions. To prevent such disruptions, we substitute the missing sensor input with a stream of historical physical states. The substitution inputs are recorded from an attack-free phase of the RV mission, and we record physical state information such as position, velocity, throttle, angular velocity, etc. We assume that an attack detection technique is already in place, which gives us an alert in real time. When an attack is detected, we replay the historic states recorded from an attack-free phase till the RV is outside of the attacker's range. And then we go back to the original sensors. And that's one of the ways we can recover from the strong attacks as well. Does this sound strange to anyone? We always thought that replay is a type of attack. And here I'm telling you that we can use replay to mitigate attacks. So let's take a quick look and understand how it really works. So imagine if the attack starts at T0 and continues till Tn. After Tn, the malicious signals are not strong enough to influence the sensors anymore. And starting T0, we start replaying the historic states. And the idea here is, instead of using bad sensor inputs under the attack, the RV will use a benign historic input. The idea is to make the RV think that it is in a past state so that the controller realizes, oh, well, I have to go a long way in my trajectory and I have to close this gap. That signals the controller to derive constant actuator signals instead of fluctuating actuator signals. That's the difference that historic state replay really does, that instead of fluctuating actuator signal due to historic state replay, we can ensure that the actuator signals are now just constant. And that ensures the RV, and it maneuvers the RV out of the attack zone safely. We started by looking at the current security mechanisms for RVs and understanding how secure are the robotic vehicles today. And we saw that detection is not a complete solution, as it does not ensure safety. This calls for better attack response. And we think that software solutions can effectively recover RVs from attacks and ensure safety. That brings me to the end of this talk. The message I want you to take away is autonomous robotic vehicles are quickly becoming popular in fast-growing Industry 4.0. And the sooner we think about security and design better security strategy, we will save a lot of pain for later. We won't have a lot of pain later. The focus should be on developing attack-resilient countermeasures that ensure safety, and low-cost software solution can offer reasonable recovery capabilities. Thank you very much. I'm happy to take questions.